Sir, you have forgot to unmute yourself. Sir, you have
Yes.
on mute.
Okay. So, thank you. So, suppose this is a tall vessel and it is self-supported. So, it is standing there by its own supports. And suppose from here there is a wind. From this side, there is a wind flowing. Okay. So, due to this wind force, okay, definitely these winds will have a thrust on it, and due to this wind force, the vertical vessels will tilt to bend. Okay, the wind will induce a bending moment. So today we will see the effect of the wind on a vertical vessel. Now, the wind load on the vessel, you write down, okay. The wind load on the vessel is given by this equation. Here we will not deduce the equation, we will use only for our designing purpose. If some of them important or needed to be established the equation, then only we could derive the equations. So PW equal to half of CD into rho VW square into A. What is the meaning of that? That is, the wind load is nothing but the PW, capital PW, and CD is the drag coefficient. CD is the drag coefficient. Next, rho is the density of air. VW obviously nothing but the velocity, wind velocity. And what is A? A is the projected area oh, what is A? A is nothing but the projected area normal to the direction of wind. Okay, so that is nothing but the projected area. So if this is a tall vessel, cylindrical, wind is flowing from this direction, so the projected area will be a rectangle, isn't it? Having the, this is nothing but d, and this is nothing but the length of the or height of the vessel. So the projected area will be a rectangle, One side is D and another is L. Now, apart from the above equation, that is the PW equal to half of CD rho VW square into A, another simplified relationship for the wind load can be like this: 0.05 VW square. So if we only know the wind velocity of a particular zone or where the tall tower is situated, if we can know the wind velocity, okay, then we can estimate the wind load by this simplified equation. Now here VW equal to the maximum wind velocity experienced by the region under forced condition in okay, these data of the wind velocity of a particular zone throughout the year can be get from the nearby airport authority. Okay, for their own purpose, they measure the 24 into 7 wind velocity of the particular airport. So this data is easily available and you can take this data for your own pressure vessel plant setup. So VW data is easily available. Now, one thing, those who are those who have know how to fly the kite, okay. So if you see or if you observe, suppose kite, those who know how to fly the, so the wind velocity varies with the height. Okay, at the ground level, the wind velocity is generally low, and if we go up, then the wind velocity increases. Okay, this is a general experience, so that's why the kite can fly at high altitude very easily rather than at the lower altitude. Okay, there are other reasons also, because in the ground level there are many high riser, okay, building, whatever. So that's why their velocity decreases also. Anyway, so the wind velocity varies with the height. So it may be shown like this for a tall tower. Suppose this is a 50 feet tower. So it may be like that the lower portion or up to this height, okay, up to this height, the wind velocity is V1, and above this height the wind velocity changes and the wind velocity is V2. So where V2 greater than V1. So it may be. Then how to estimate that this type of problem, whether there is a deviation or changes in the wind velocity? So in this case, we will calculate or estimate the wind load and bending moment like this. Load or wind load, whatever, wind due to load due to wind acting in the bottom portion of the vessel. So we can calculate BW means bottom wind. So that is a constant K1, Kn to K2, another constant P1, H1, T naught, where you write down the PVW is nothing but the total force due to wind, total force due to wind load acting on the bottom, acting on the bottom. Next, what is D naught? Is the OD, outside diameter of the vessel, including if there is an insulation, so including that insulation thickness, including the insulation thickness. What is H1? H1 equal to height, H1 equal to height of the bottom part, height of the bottom part of the vessel, height of the bottom part of the vessel. Okay. What is K1? K1 and K2 are that safe factor. This is a constant. Okay. K1 values is generally 1.4 for flat plate or flat surface. Its value is 0.7 for cylindrical surface. So tall tower cylindrical surface, so 0.7. Okay. And what is K2? K2 value is also depends on the cycle of vibration of the vessel. Okay. If there is some seismic vibrations, okay, so that vibrations represent the K2 coefficient, and generally it is nothing but 1. If it is not given in the problem, so you will take K2 value is equal to 1. Okay. And similarly, so up to this, this is the height H1, and up to this is the height H2, and the total height is H. Okay. So H equal to, capital H equal to H1 plus H2. Now, similarly, we can find the load due to wind acting in the upper portion of the vessel that is the H2. So P UW equal to similarly K1, K2, P2, H2, D naught. Now, so these are the wind load PBW and PUW. Now these wind load, what will happen? It will try to bend the pressure vessel. So there will be always a bending stress and a bending moment. So we will calculate the stress due to bending moment. Due to bending moment. Okay, so MW is, okay, it will be PBW into H1 by 2 if the H value is less than equal to H1. Okay, so total value is less than H1 or equal to H1, so this equation valid. And otherwise, what will be? The bending moment will be PBW H1 plus 2, H1 by 2 divided plus PUW H1 plus H2 by 2. If capital H is greater than H1. Okay, so from this we can calculate the bending moment. And what will be the bending stress? The bending stress will be, therefore the bending stress due to wind, bending stress due to wind load in the axial direction will be F. It is nothing but 4mW divided by T is the thickness of the pressure vessel, Di plus T into Di, or we can write also 4mW by pi d naught squared into T or d squared into T. Okay, so these are the stresses induced due to the wind load. So if we solve a problem, okay, everybody try to solve this problem. You try to solve it, write down a tall vertical column 2.5 meter in outside diameter and 42 meter in height is to be installed. Operating temperature and pressure are 160 degrees Celsius and 4 kg per centimeter square gauge pressure respectively. Okay, other specification as insulation thickness, equal to 120 millimeter. Okay, allowable stress or permissible stress, of the material or the shell equal to 780 kg per centimeter square. We have given the joint efficiency at 0.8, corrosion allowances as 1.5 millimeter. Again, density of the cell material is 7600 kg per meter cube. Density of insulating material is 500 kg per meter cube. Then you write down this data, although not needed for this problem. Anyway, it has a part 2 problem. It has a second part. Weight of ladder is 30 kg per meter. Wind force acting, that is the wind pressure, 110 kg per meter square. Weight of 280 millimeter outside diameter pipe equal to 60 kg per meter. Now you calculate the bending stress. induced due to the bending moment of due to wind. So calculate the stress induced due to wind load. So find out. You see the formula and calculate the bending stress. You calculate. I will ask. Rule number 1.
One present, sir.
बस रोल नंबर बोलो. Roll number 2.
2 present.